Okay, for this last lesson in Physics 12, and for this topic is basically looking at some applications. So one of the reasons this topic is so important is because this discovery of electromagnetism, the connection between current and magnetic field and vice versa, it allowed the creation of two very important things to humanity. One is called the generator, and one is called the motor. So the generator basically takes motion and creates energy, where the motor will take energy and create motion. So this one goes one way, the other goes the other way. And this is an amazing discovery. Just think of a BC Hydro dam. That's a giant generator. You have these giant turbines that are rotated using falling water, and it causes it to rotate, and you have these huge coils of wire around it that through that rotation it creates mass amounts of electricity that is able to power our cities. And of course, motors, anything you have, anything you want to turn, that's a motor. So anything we want using electricity to turn something, we need motors. So there's some parts of a generator. We have the rotating armature, and we have slip rings. That's for AC and DC. I'll try to go over this. There's some good videos you should watch too. Hopefully this link still works. But you can notice how, depending on how, well, if you look at this first one, we see there's these two metal rings. So this first metal ring is connected to the blue wire, and this second metal ring is connected to the other side, that other end. Again, technically the blue and the red is a single wire, but it's showing the left and right of it. So this one will create what's called alternating current. Now, on the next page, we'll go into more detail how we know which way the current is moving. But basically, to break it down, is that, again, if you picture, you kind of have to picture a single charge, positive charge, somewhere in that wire. If you know where a single charge will go, you know where all of them will go. So this is for a generator. So we're saying this thing is going to be rotated counterclockwise. So if you know the velocity, in its direction, so the velocity, this blue thing is going to go up, and the red is going to go down, right? And if we know the direction of the magnetic field, using a right-hand rule, we can then determine will the current go in this direction around it, or will it go in this direction around it? But basically, because of how these loops are connected, as when it's in this orientation, the current's going to go one way, but when it's flipped 180 degrees, it's now going the opposite direction. So it goes back and forth, back and forth, back and forth, back and forth. Where in this DC generator, how it works is we have a single ring, but notice how it's broken right in the middle. It's not connected right there, right in that middle piece. So what happens in this case is when this loop rotates, we always have the left side connected to the left piece, metal piece. The right side is always connected to the right middle piece. You end up getting the current to always be in the same direction. So let's just go over how we can determine which direction our current is going to go in. Okay, so let's say we have, here's our loop. And this thing is going to be rotated in this counterclockwise direction. So what that means is the right side is going to have an upwards velocity, and the left side is going to have a downwards velocity. And our magnetic field, we're going to say, is going to the right, just like in those pictures. So our magnetic field is to the right, like so. Okay. So if we use our right-hand rule, again, we're going to stick our index finger in the direction of velocity. So I'm going to look at this point right here. Our index finger is pointing up. Our magnetic field, so our middle finger is going to be pointing to the right. That means our force is going to be in this direction. So our current is going to end up traveling, looping around like so. Okay, this is the direction our current is going to travel. Okay. So we get maximum EMF when our velocity is perpendicular to our magnetic field. But we know that because this thing's rotating, eventually this thing is going to have this upright orientation as it rotates. So now this thing is still rotating in this counterclockwise direction, but at this point our velocity looks like so. Here's our velocity vector, and up here it's our velocity vector. Our magnetic field hasn't changed, still traveling to the right. There's our B field. But at this point we can see that when the velocity is parallel to our magnetic field, we get a minimum. Okay? So we get this maximum value of flux. We get 0. Okay? So it comes down to the zero equation. EMF is equal to B times L. So the length that's within, length of the wire that's within the magnetic field times the velocity. But what we need to notice is that there's technically two wires. There's the right side of the loop and the left side of the loop. These up and bottom parts don't matter because those parts are they're not relevant. They don't have, well, they think of that thing as outside the magnetic field. Just these length of wires that is perpendicular to our magnetic field, that's the wire we're interested in. So we end up, because we have the left and right side, it's multiplied by 2 for this generator or motor. And usually we just don't have a single loop wire. We have loops and loops and loops of wire. So times the number of loops, there are a number of loops, right? And then we have our BLV, and then at different points of the rotation, that's where we get the sine component. So using that equation, we can kind of get an idea of what's going to happen. So this is more like what a generator or motor would look like. We have coils and coils and coils, and you have multiple. So the one we just looked at, a very simple case, was just a single loop of wire. If we just have a single loop of wire, we're going to get a current or a voltage that looks like this. So you're going to have points where you have lots, like if you had, basically we're charging a light, if you're powering a light bulb like this, it would be flickering on and off non-stop, and it would probably give you a migraine. So how do you avoid that? So what's going to happen is if we use a DC generator, it's going to look like this. But how do we get rid of this, like these points of minimum? So what's going to happen is if you have, instead of just having a single loop, you're going to have another loop that is perpendicular to it. Right, so you think of it, or think of a front view. Here's our first view, and then you have one loop going like this, and you have another loop going like this, another loop going like this, another loop going like this. You're basically trying to fill in all those gaps, make sure you have no holes. So you have all these loops of wire in like at many different angles, and as you get more and more of them, it starts to get rid of those zeros until eventually you're just going to have a flat line. And there's different ways you can create these motors. Sometimes you have the coils outside and you have a magnet that's rotating, or you can have the coils are rotating and the magnet's outside. It doesn't really matter. They both work. It just depends on, I guess, depends on the scenario and what's easier to make.